This is the video lesson on matrix manipulation. In this lesson we're going to be learning different ways of manipulating matrices to actually put them together and different sorts of things like that. So we're going to be going over addition and subtraction, scalar multiplication, transposition, matrix multiplication, and finally we're going to end off with just a special type of matrix multiplication or block multiplication. So starting off with addition and subtraction. The only conditions for addition and subtraction are that the two matrices being added or subtracted need to be of the same size. And if this is the case, the new matrix is going to be, again, of the same size, and it's simply the addition or subtraction of the corresponding elements within each matrix. So, let's say we had a matrix, A, and we subtract a matrix B. To write that in IJ form, we're going to basically just have resulting matrix, where, as I said, the corresponding entries of B are subtracted from the corresponding entries of A. Just as a quick example, if we have a matrix 1, 2, 3, 4, and we subtract the matrix 0, 1, 2, 3, the new matrix is going to be the same size, so 2 by 2. Again, just as a quick check to make sure before you do addition or subtraction, these are both 2 by 2, which is why you can go with the subtraction. Simply going to be 1 minus 0 for that first entry, which is 1, 2 minus 1 for the second entry, or 1, 3 minus 2, which is 1, and 4 minus 3, which is again 1. So new matrix, 2 by 2, 4 entries. Each entry is just first entry subtracted by corresponding entry in the second matrix. That's addition and subtraction. Very simple. Next, scalar multiplication. Scalar multiplication is also very simple. There's no conditions on the size of the matrix. Basically, if you have a matrix A and you multiply by some scalar K, it results in just a matrix where each entry is multiplied by that scalar K. So very simple. As an example, if we had 2 times our matrix 1, 2, 3, 4, we're simply going to multiply 2 by each entry. So 2 times 1 is 2, 2 times 4, 2 times 2 is 4, 2 times 3 is 6, and 2 times 4 is 8. The new matrix again will be the same size, and other than that, very simple. Just as a quick note, if you ever have, say, negative A, one way of looking at it, or if you're subtracting A, is it's like negative 1 times our matrix A. So it's like multiplying by a scalar rather than subtracting that matrix. That's scalar multiplication. Now we're going to look at transposition. Transposition, we'll deal with it a little more later on in the course, but basically what it is just a matrix where the rows have been replaced with the columns. So if we have a matrix A, the transpose of that matrix is noted with a T, superscript T. And what that means, as I said, if A is initially Aij, the transpose of it is Abi. So if an entry was at 2, 3, it's now going to be at 3, 2. So as an example, let's say we had our matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. If we want to find the transpose of that matrix, simply a new matrix where that first row is now our first column, 1, 2, 3. Second row is our second column, 4, 5, 6. And our third row, 7, 8, 9, is now going to be our third column. So that's one way of doing a transpose. Another way you can look at it is if we draw a line along the main diagonal, so it should have gone through that 5 and 9. If we draw a line along the main diagonal here, yeah, that's okay. Basically, the transpose is like a flip over that main diagonal. So drawing that same line here, you can see that our 4 and 2 have switched, our 7 and 3 have switched, our 8 and 6 have switched. And so, if a matrix is equal to its transpose, we can say basically that it's symmetric. That's how we denote a symmetric matrix, because it's symmetric along that main diagonal. You probably would have seen this little t before with questions and such for vectors, where you have a vector 1, 2, 3, but when it's written in textbooks and things, a lot of times it's written 1, 2, 3 transpose. And again, that just means the same thing. So this row is actually the first column, or the only column in that vector. That's it for transposition. Now we're going to move into matrix multiplication. So this is quite a bit more complicated than the previous manipulations we've done. But once you get used to it, it's not too bad. So it's just the beginning, it will seem complicated. But matrix multiplication has a couple conditions we need to satisfy in order to actually be able to multiply two matrices. You can't just multiply any two, just like you can't just add any two. They need to be the same size. For multiplication, there are different conditions. For multiplication, if we had a matrix A, which was m by n, and a matrix B, which is n by k, we can only multiply these two matrices if the number of columns of matrix A, so we can only do A times B, if the number of columns of matrix A is equal to the number of rows of matrix B. The resulting matrix will have the same number of rows as matrix A and the same number of columns as matrix B. So that sounds complicated, but the easiest way that I can think of to do this is simply write out their dimensions. If you want to figure out if you can multiply A times B, write out the dimensions next to each other. So you have m times n times k. As I said, the number of columns of A has to equal the number of rows as B, or these inner two dimensions have to be equal. So in this case, you have n by n, it works. The resulting matrix is going to be the number of rows of A and the number of columns of B. So you're going to end up with an m by k matrix. So you may not understand why this works just yet, but once I start showing the multiplication itself, it will make a little more sense. So in this case, if we wanted to multiply B times A, we'd have n by k and m by n, and right away you can see these two aren't the same, therefore this can't be done. So to multiply matrices, let's say we had a matrix A, which is 1, 2, 3, 3, 2, 1. And we can see it's got 2 rows and 3 columns, so it's 2 by 3. And if we have another matrix B, which is 1, 3, 1, so here we've got 3 rows and 1 column, we can multiply A times B, because then if we look at the dimensions, 2 by 3, 3 by 1, got the same inner dimension, and our resultant is going to be a 2 by 1 matrix. So there are different ways of doing the multiplication. The way I like to use is write out your first matrix. So to do A times B, we're going to write out A, 1, 2, 3, 3, 2, 1. And we're going to write out matrix B starting at the bottom right corner of matrix A. So we've got 1, 3, 1. And now our resulting matrix, we're simply going to draw it above matrix B to the right of matrix A. So it's simply going to be this matrix here. As we can see, it's going to have the same number of rows as A and the same number of columns as B, which is what our conditions were to start with. To get these actual entries, we're going to be using the dot product. So to get our first entry, we're going to look at the corresponding row in matrix A, so we've got this row here, and the corresponding column, well, we've only got one column in matrix B, but if we had more than one, we'd look at the corresponding column. We're going to simply do the dot product of this row with this column to get that first entry. So here we can say 1 times 1 plus 2 times 3 plus 3 times 1. And that's going to be 1 plus 6 is 7 plus 3 is 10. Now to get the second entry, we're now in the second row and still in that same column. So we're going to now have, taking this out, we've got 3 times 1 plus 2 times 3 plus 1 times 1. Oh, I already did a plus 1 times 1. So it's going to be 3 plus 6 is 9 plus 1 is 10. So our result, we can say A times B is our new matrix 10, 10. And this works just the same with more complicated matrices where you just look at your corresponding row, corresponding column, do the dot products, and that's it. That's why I like to use this method. Because if you're writing it, if you try to right away get the result from these two matrices, it's very simple to get confused on which row you're supposed to be doing the dot product and which column and so forth. So that's it for that. Now, when it comes to multiplication, when we're multiplying regularly, we have 1. If we multiply by 1, it keeps the same matrix. Our 1 for matrices, as you would have learned previously, is our identity matrix. So we're just going to go through some more multiplications just so you get some more, just so I can show it a little more, and to see that the identity matrix in fact is like a 1. So if we had a matrix 1, 2, 3, 4, 5, 6, if we wanted to multiply by an identity matrix, we have to first choose the identity matrix of the appropriate size. So we know it's going to need to have the same number of rows as the number of columns in our matrix. So it's going to have 3 rows. So 1, 0, 0, 0, 1, 0, 0, 0, 1. And the reason for that condition, as you probably would have figured out by now, is because in order to do dot product, you need a corresponding entry. So if this had one more row, you couldn't do the dot product of this column with this row. But moving on, with this multiplication here, our new matrix is simply going to be in here. So we've got 2 rows, 3 columns now. And for each entry, we're going to have, for this first entry, we're going to be looking at the first row, first column. So it's going to be 1 times 1 plus 2 times 0 plus 3 times 0. So it's 1. Next, we're going to be looking at the second column, first row. We've got 0 times 1, 1 times 2, 0 times 3, so 2. And this pattern will follow all the way through where for the next entry, these zeros will be times 1 and 2, and 1 times 3 will give us our 3, and so forth. And we'll end up with the exact same matrix that we started with. So for these bottom ones, basically, it's just 4 times 1, 5 times 0, 6 times 0, and so forth. And as you can see, the reason why we only have 1s along the diagonal is so that we have this effect. If we had all 1s in this matrix, because you may think, well, shouldn't that be the matrix that acts like a 1? If we had all 1s here, this would actually be 1 plus 2 times 1 plus 3 times 1, so it would be 6 instead of a 1, which is what we don't want. So there's the identity matrix. And the same thing goes for the 0 matrix, where if you have a matrix of all zeros, if you multiply it by any matrix, you're going to end up with a new matrix of all zeros, because doing that dot product, you're just going to be adding some component times 0, all 0. Now we're going to look at block multiplication. So block multiplication, it's not used very much throughout the course, but if you ever see a case where you can use it, it works perfectly. You're more than welcome to use it. So let's say we had a matrix, big one here, 0, 0, 4, 5, 0, 0, 6, 7, 1, 2, 1, 0, and 3, 4, 0, 1. and we want to multiply this matrix by another matrix, 1, 2, 0, 1. Now we can just do this the regular way, where we bring this matrix down and start creating our new matrix. But it could get quite complicated because it is quite a long multiplication. So another way you can do it is with block multiplication. And what that does is, if you notice smaller matrices within a matrix, you can actually cut it into blocks to use those special matrices. So if I cut it right here, we can see that in the top left we've got a 0 matrix, in the bottom right we've got the identity matrix. So we can actually write this as a new matrix where we've got the 0 matrix. We'll call this 4, 5, 6 matrix matrix P. This matrix we can call matrix Q. And this bottom right one, as we can see, is an identity matrix. And then, since we divided this matrix in half, we have to do the same thing with this one. So we can call this new matrix simply X and Y, where X is 1, 2, Y is 0, 1. So now when we're doing the multiplication, we're going to get a new matrix. And if I wrote this out, just to follow the same steps we were previously, times xy, we'd end up with 0 times x, and as we explained before, 0 times any matrix will be 0, plus p times y, so we're just going to have p times y, q times y, x, plus I times y. And I didn't explain it before, but if we multiply the identity matrix before a matrix or after a matrix, they will have the same result. Sometimes you will need different size identity matrix, whether you're before or after, depending on if the rows or columns are different, but it works just the same. So now we have this new matrix, py, and then qx plus iy. So we can actually write that out, where py, we've got p is 4, 5, 6, 4, 5, 6, 7, and y is 0, 1. And at the bottom we've got qx, so we've got 1, 2, 3, 4. X is going to be this top part, 1, 2. And we're adding I times y, or just adding y, so we're adding 0, 1. And if we work that out further, it's going to be equal to, performing this multiplication at the top, we know the resulting is going to have 2 rows, 1 column, and it's going to be 4 times 0 plus 5 times 1, so it's going to be 5 here at the top. And then we've got 6 times 1 plus 7 times 1, which is going to be should be 6 times 0 plus 7 times 1, which is going to be 7. So as you can see, I got confused there having it this way, but you could always write it where they're offset, and it makes it simpler. At the bottom we've got 1 times 1, it's again going to be 2 by 1 matrix. 1 times 1 plus 2 times 2 is going to be 5. And then we've got 3 times 1 plus 4 times 2, or plus 8. So 8 plus 3 is going to give us 11. We're adding 0, 1. And that's going to give us a new matrix, 5, 7. And then we've got 5, 12 at the bottom here. That's 11 plus 1 and 5 plus 0. And that is our resulting matrix. And that would be the same matrix as if we just multiplied the original 2. So that is it for block multiplication, and that's it for the video lesson on matrix manipulation. Some of the stuff, there are theorems and such for multiplication, all that, transposition. They are in the appendix for your reference whenever you're doing tutorials for class or anything like that. Other than that, that's it for this lesson.